Chinese researchers have published a new LK99 room temperature superconductor paper. Is this a real breakthrough? As you recall, we made a video 2 weeks ago on the Korean LK99 work. How do the Chinese and Korean work compare? Randy and I will review and discuss.
So, Brian, before we get into the deep weeds, which we're really going to get into deep weeds today, I think maybe there'll be new people that are just coming on board. And we've talked about this before, but just quickly and briefly, why is this important? What in the heck is it going to do for humanity if this LK99 really is a room temperature superconductor?
So a room temperature superconductor will change everything related to energy and electronics. In particular, computers can get 800 times faster, or 200 times faster, and because they'll go from 4 gigahertz of compute speed up to 800 gigahertz or even a few terahertz of speed. And this has been done with really cold, like near absolute zero levels of temperature. So getting that temperature is very costly, but what you can produce from it is so valuable. The levitating trains, better magnets for particle accelerators, that even with the difficulties of getting to super cold temperatures, that has already been an $8 billion industry.
And you also,
if we can get to full room temperature superconductors, then we can possibly make far easier nuclear fusion reactors, the faster computers. So it's potentially highly valuable when we can get it.
And you mentioned the other day that if this stuff really works, that maybe not this year, maybe not next year, it might be a few years, but if they could even just get a thin film of this, they could put it onto existing chips, which would accelerate their capabilities dramatically.
It would be new chips in general, unless you were to hybrid them in there, which you could potentially with this, where you can make a few superconducting circuits on a regular chip and go side by side with the regular CMOS chip. The reason you can do that would because you wouldn't have to freeze the whole thing in some super refrigerator. Here, because room temperature, you can just leave it in a regular data center. So integrating the new chips, the new capability with regular technology would be far, far easier if you remove the issues of, I must make a super cold refrigerator costing tens of millions of dollars. I must put things into a diamond anvil, which some of the other superconductors need to do. It just makes it easier because, just like me in this room, I could have it work. Versus for all the other ones, you need to have really expensive, difficult special equipment. I don't think you or I or anyone else listening has encountered a liquid nitrogen, liquid hydrogen cooling chamber, right? You don't run into it.
Probably not. So let's take a look at that paper then. So you want to
Okay. So here's a snapshot of the paper from the Chinese team. So we know it's real. You don't need to look at it because it's just describing their observations, what they call, of diamagnetic strange metal phase in sulfur, copper, co-doped lead apatite, co-doped. So even the title is confusing and difficult to understand. So we'll have to explain all that stuff. So basically it's different materials and they added in some copper and sulfur. So the main results, and again, these results are difficult to read, but basically they have magnetic detection of the key property of superconductors, which is the Meissner effect. Meissner effect is where you have a regular magnet and you stick a superconductor over it and it floats and locks in position, right? But the Chinese have not achieved the full Meissner effect where you can put a superconductor below on top of a magnet and have it lock in place. But they've detected from these readings the magnetic telltale signatures of the Meissner effect. Okay, so basically they detected a lot of the smoke
Okay.
of that. Yes.
Okay, so let me understand. So they've made some particles that they
Yeah.
believe in using the technology that the Koreans have presented in their papers. They've made some particles. They haven't been able to get them to float like the Koreans have, but they're using different techniques, measuring systems that are measuring what's taking place in these particles, which also show that they're on the right track.
Right. Right.
Okay.
So, Berkeley Labs, the national lab for the United States, has top simulation researchers. One of them has written two papers in support of that this stuff works. They put it into a supercomputer and said, when we do this DFT density function theory modeling of it, when we look at these materials look very interesting for doing superconductors. We think there's a there,
Right.
right? From, the most prestigious lab in the United States and from top level researchers. That theoretical researcher talked to the experimentalists who were also at the lab, and the experimentalists said the Chinese work on this stuff, from their previous paper, looks really good. It looks thorough and meticulous. So the Chinese approach is to do the work of magnetic analysis that is precise. They do microwave absorption and other stuff. So they detect all around what the materials should be. Like all of the superconductors do this in terms of magnetics. And so we've said we're detecting all these other features as opposed to going for the flashy demo,
Right.
right? We're doing dotting all the I's, crossing all the T's to get the material. One of the reasons that they're doing this is because they're making nano powders of this stuff, right? So very tiny powders of the material, and it is not pure. If it was pure, they could take up a flake, like the Koreans, and float it, right? They have not got to that level. And they're saying, if I have a bunch of nano powders, then what are the respected tests that I can do, still difficult, do to get the readings that show that this is happening,
Right.
right? So they are doing meticulous work to do that. They also do meticulous work to prove that the three other accusations of it's copper sulfur, that you made a mistake, it's transparent, this or that, the two or three other things that the critics say, the scientific critics say, this is not superconductor, it is A, B, or C.
Right.
And so they've done the work to say, here's why it's not A, here's not B, here's not C. Again, difficult work that doesn't result in a flashy demo. It just says to the other scientists, see these readings? It's not that. See these readings? It is this, right? So that is the work that they're doing, is to grind through and say, the tough work of science. Right. It's not flashy. It's like, I'm doing tests. So the other thing that they did, they improved how they made the materials. So this, again, don't look at this process unless you plan on actually making it and reading the 5 pages describing their process. But the detail which they describe their process is very useful, again, for other scientists to say, and their audience is other scientists to say, hey, here's the real deal. We're going to tell you how to copy what we're doing, which is the whole point of publishing a paper, is to say, here's how I'm doing it. You can do it too, and then you can believe me. So then, yeah.
So Brian, in the early days when we were first reporting on this, you were talking about how somebody with a fairly sophisticated high school lab could do these things.
Right.
Are the Chinese still at that level? Are these things that a sophisticated high school lab could do, or have they moved up to something more?
They moved up into something else, right? Yeah, the whole high school lab could do it. That was
no
a red herring.
Okay.
No, yeah, I can't make a Michelin star 3-star meal, and I can't do this either.
Got it.
right? But much other people can't. So it's again not easy. And then the difficulty with it is that if you can make it, doing the work to prove that you make it is even harder.
Right.
And these guys also do not have good enough equipment to fully analyze and prove that they have done it, which is another problem, is that because the rich labs with the really good gear have not gotten really into this, is that some of the proofs kind of go down to a certain level. And it's like, well, I'm a professor. I know what I'm doing. I'm in a decent university, but I don't have the $1 million X machine or $10 million other machine, right? Because I don't have it yet. And then the guys with that machine are saying, I'm not ready to give you time on these other machines yet, right? I'm not willing to spend a few months or a year working with you. Get further along, and then we'll talk. So again, it's not high school people working on it. It's top, like Beijing University. It's not a no joke institution, but if you go to every department, every physics department doesn't have, semiconductor analysis equipment or, able to measure down to some super low level. Right. So, so they also did, so of this slide, although it's difficult to read, the thing on the black blob on the left corner is showing the powders at high magnification. And then they also say that there's when they put pressure on it to make it into something like a hexagon, then there's some kind of directional stacking, right? Which basically means that they're getting something that they want, shaping it into, these larger pieces and under pressure, and then they can put them together. So they think that is the way to go to making this purer and better, is to put these together into tablets and to stack them and then to do other work. So it's so it's under 25 hours of pressure, all that kind of stuff. So again, not easy work, and I don't admittedly fully understand exactly how this kind of all comes together, but they are grinding forward, figuring out a tough problem, several tough problems, which we'll discuss a bit more at the end. And then here's a picture showing how they measure the sample. Again, they have some electronics, a little set of sensors and diodes, and then the two black pieces are the actual material that they've put on to get their resistance measurement. But again, this is not the super expensive equipment, right? But it is non-trivial equipment. They're doing real work, right? So just an aside, when I wrote about this on my website, some people said, well, how come they didn't get the multi-million-dollar equipment and just settle this thing and then do the work? And their excuse of, well, I can't put electrodes onto the powder, I can't do this and that. They say, well, get the $1 million equipment. We do it with semiconductors in the multi-billion-dollar semiconductor industry, right? So it's showing that they're showing pictures of, here's what we're doing. We're not hiding anything. And I don't have this gear. This is not a multi-million-dollar hunk of equipment, right? But it is precise equipment up to a certain level. And they go to the level of that equipment with their results.
Right. And speaking of your website, people should obviously be checking out your website at nextbigfuture.com, right?
Yeah.
And it is, after all, the biggest and most successful science blog in the known universe. All right, back to
Thanks, Randy. So here's the summary of the research. Again, complicated results. But I'll try and summarize. If people want to look at it, again, links to the paper, link to the supplementary work. Other links, we'll have that in the description. So the summary of the research is, point one is they improved how they made it. They added in their process a way to put in more sulfur and copper to get better results. The better results that they got, the hysteresis loops, is again this other feature of if I have Meissner effect, I will have hysteresis loops. So even though I can't fully detect the Meissner effect, I detect the hysteresis loops, and the detection of that hysteresis loop is stronger than what they did in January. So they improved how they made it, and they got a stronger signal on this key effect. Mm-hmm. And then the resistance temperature curves that they have says it shows a strange metal phase at large current. So again, they're figuring out what's happening. So there's multiple phases of materials going on, and they've detected, strange metal phase. So again, making progress of untying the knot of the problem. Right, it's complicated, and so here's another thread that I'm pulling out. I'm finding that there's this other stuff going on. So defining the problem, figuring out what's going on, making progress on those 2 points with difficult, precise, painstaking work. And then they also describe some weak field voltage and superconducting vortex dynamics that all makes them confident. They detect these things, so they think they're on the track to figure out this room temperature superconductivity. Okay. So it's incomplete work, but it is making progress. So for me, my interpretation of this is that for the naysayers who say, well, they haven't done the full thing, they haven't got everything yet, is because it is a hard problem. Everyone else who is working on room temperature superconductivity, the guys using diamond animals, they're taking years to do their tests. It's always understood to be hard. It's very difficult to detect. And the whole it's easy is one of the wrong things. It is not easy. It's a hard thing to do.
Okay.
So before we go to the Korean work, let me summarize this thing. So they figure out how to make things a bit better. They're adding in sulfur and copper. They are doing this magnetic detection, magnetic effects properties in a very precise way. And their theory is that there is a superconducting phase underlying these other phases. And those other phases is what the other guys were detecting. Okay. They also converted it from an insulator at the beginning. When they dipped it into sulfur, they got it down to about graphite levels. So it didn't get all the way to superconducting resistance. But you start from an insulator, which is like an anti-superconductor, and then you get it down to the metals, and then you get it down to superconducting. So they're on the way. But the naysayers who say it's not a superconductor, it's an insulator, they stopped it at step 1, which said it's an insulator. Then you have to do other work to it to get it to not be an insulator, to get it to at least as good as metal. But the thing is, if I converted a pile of powders into the resistance of a metal, like copper, right? Or graphite or whatever like that, that's an amazing thing. And the researchers discuss and say, this is amazing. You turn powders, insulator powders, into non-insulator powders, which it's like metal conductivity, but it's not a metal, not like a wire of copper. It's a powder, a bunch of nano powders, which is like, show me another pile of nano powders that you turn into the conductivity of copper, right? That's why they say that there's superconducting in there, right? And then they think that if they get pure, they can get to superconducting levels. So again, for the Korean work, they've taken a pure flake and then they got it to fully levitate, which is the full Meissner effect, right? So both teams, multiple teams, 2 teams in Korea, maybe up to 10 teams in China, are making progress. So the last thing is, what is the US doing? What Europeans, these other researchers are doing? I don't know what they're doing, right? Because they have only published, some groups have published things that are negative, right? Yeah. I know that the Air Force Research Lab funded a small group at Chapman University to work on thin film. They have not published yet. There was rumors from the Chapman University person that there was some larger military funding, DARPA, Air Force Research Lab, don't know what's happened with that. Easily something could get funded, we wouldn't know about it. I would expect that if China is working on this, at some point, the US would do a just in case, let's do some serious work on this thing just to make sure,
Yeah.
right? Because
You can't be behind on this.
yeah,
This is almost Sputnik level where you can't let the Chinese be first or the Russians or the Iranians. This is
right.
something that the US needs to be at the very forefront. And so I can't imagine that there has to be stuff going on right now that we're not aware of at that level.
Right. So lastly, summarizing the questions from the beginning, is this the real breakthrough? No, it is not the real breakthrough. There's still a lot of work to be done, but it is real. They're making progress on it. They're detecting things that give us, give me confidence that results will continue to come out. Progress will be made, but it can be a long process because it is hard. Like, why would you expect a, you know, one of the top goals of physics and material science, removing Excalibur from the stone, to be easy?
Yeah.
That's the wrong expectation, right? But if Excalibur budges, then it's like, let me keep trying.
Yeah.
It budged.
All
So
right. So, by the way, we certainly invite your comments and questions, just like on the blog. Lots of comments and lots of questions. That's what makes it really exciting for other fellow, members of the community. This is breakthrough stuff. We try to bring you breakthrough stuff all the time, and the comments and the questions really help us to know stuff that we would not otherwise probably be able to come in contact with.
okay, thank you, Randy.
Okay. It's been great.
Okay.